Hey everyone, welcome back to another video. So today I'll be explaining physics paper 3 extended code 0625 paper 31 October-November 2014. Let's get with the first question. Question 1 part A states figure 1.1 shows a distance time graph for three different objects which is A, B and C. Distance over here we have the figure 1.1. Question states describe the motion of each of the objects A, B, and C by selecting the appropriate description from the list below. So the constant speed, increasing speed, and decreasing speed, and stationary. So you have to choose one of these from for each letter. So for A, it's a increasing speed. So answer will be increasing speed. For B, it is constant speed, and for C, it is stationary. So this is what we will do in part A of question 1. Question 1 part B states figure 1.2 shows the speed time graph for three more objects D, E and F. Describe the motion of each of the objects D, E and F by selecting the appropriate description. So from the list below. So over here we have the constant speed, constant acceleration, increasing acceleration and stationary. So for D, it's an increasing acceleration. For E, it's a constant acceleration. And for F, it's a constant speed because there is no increase in speed over the time period. So this is what we will do in part B of question 1. Question 1 part C states figure 1.3 shows a person bungee jumping from a bridge. The person is attached to an elastic rope. So this is the figure 1.3. So part 1 states in figure 1.5, in 1.5 seconds, the speed of the jumper increases from 0 to 10.5 meters per second. Calculate her average acceleration during this time. So A is equal to V minus U divided by T. So the final speed was 10.5 minus starting speed was 0 divided by 1.5, which is 7 meters per second squared. So the acceleration is 7 meters per second squared. Part 2 states at one point during the fall she reaches her maximum speed. So question 1 state her acceleration at this point. So at the maximum speed there is no increase in speed. So when there is no increase in speed, the acceleration will be 0 meters per second. Part 2 states what can be said about the forces acting on her at this point. So the upward and downward forces are equal, so no resultant force is acting on her at this point. So this will be the final answer for part 2. Question 2 states a diver climbs some steps onto a fixed platform above the surface of the water in a swimming pool. He dives into the pool. Figure 2.1 shows the diver about to enter the water. So this is figure 2.1. The mass of the diver is 65 kgs. The platform is 8 meters above the surface of the water. So this is the height. Part A states calculate the increase in the gravitational potential energy of the diver when he climbs up to the platform. So the GPE formula is GPE is equal to mass times gravitational potential energy multiplied by height. So 65 multiplied by 10 multiplied by 8, which will be 5200 joules. It is important to write joules because if you don't write the measurement, 1 mark will be cut over here, or half mark. Over here it's 1 mark, so 0.5 marks will be deducted. Part 2 states the speed at which the diver hits the surface of the water, ignore any effects of air resistance. So the equation will be gain in kinetic energy is equal to loss in gravitational potential energy. So KE or kinetic energy formula is 1 over 2 mv square is equal to GPE formula is mgh. So V square is equal to 2gh and V is equal to 2gh to the whole square root. Answer will be 12.6 meters per second. So the speed will be 12.6 meters per second. Part B states in another dive from the same platform, the diver performs a somersault during the descent. He straightens and again enters the water as shown in figure 2.1. Discuss whether the speed of entry into the water is greater than, less than, or equal to the speed calculated in A part 2. Ignore any effects of air resistance. So the answer will be as there is no change in distance fallen, so the speed remains the same. The loss in GPE is equal to the gain in KE, which results in the same speed. So this is what we will write in part B of question 2. Question 3 part A states the figure 3.1 shows an oil can containing only air at atmospheric pressure. Question states atmospheric pressure is 1.0 times 10 to the power of 5 pascals. The pressure of the air in the can is reduced by means of a pump. This can collapses when the pressure of the air in the can falls below 6000 pascal. Explain why the can collapses. So the answer will be pressure on the outside surface is greater than the inner surface, which causes the greater force from outside to collapse the can. So this is what we'll write in part A or part 1. Part 2 states the surface area of face X of the can is 0.12 meters squared. Calculate the resultant force on the face X when the can collapses. So the pressure is equal to force divided by area. We have to calculate the resultant force or F. So F is equal to P times A, pressure times area. So pressure is 1 multiplied by 10 to the power of 5 minus 6 multiplied by 0.12, which is 11,280 Newton. So the resultant force on face X when the can collapses is 11,280 newtons. It is important to write newtons so that you can get full marks in this question. Part B states the mercury is poured into a U-shaped glass tube. Water is then poured into one of the limbs of the tube. Oil is poured into the other limb until the surfaces of the mercury are at the same level in both limbs. Figure 3.2 shows the result. So this is figure 3.2 over here. Part 1 states state a condition that must be true in order for the mercury surfaces to be at the same level in both limbs of the tube. So the answer will be pressure of the oil is equal to pressure of the water. Part 2 states the height of the water column is 0.25 meters. The height of the column is oil column is 0.32 meters. The density of the water is 1000 kilograms per meter cube. Calculate the pressure exerted by the water on the surface of the mercury. So formula is P is equal to dGH. So density is 0.25 multiplied by 10 multiplied by 1000, which is height, and then we will calculate the formula, which is 2500 pascals. So the pressure of exerted by water on the surface of the mercury is 2500 pascals. Part 2 states the density of the oil we have to calculate density of the oil. So density is equal to pressure divided by gravitational force multiplied by height. So 2500 divided by 1000 multiplied by 0 multiplied by 10 multiplied by 0.32, my bad. So the answer will be 781.25 kilograms per meter cube. So the answer will be 781.25 kilograms per meter cubed. So this is what we will write in as the density of the oil. Question 4 states figure 4.1 shows some of the apparatus that the student uses to determine the specific heat capacity of aluminium. So this is the figure 4.1 that the student uses. Part A states state the measurements the student needs to make, including those from the electric circuit. For each quantity measured, state a symbol. So the answer will be mass of the block. M will be the measurement unit. Then initial temperature costa 1 and the final temperature costa 2. Then time of heating, which is T, voltage, which is V, and current I. It's very important to memorize all of these because this will be the most favorite topic for the examiner. Part B states use the symbols from A to complete a formula used to determine the specific heat capacity C. So C is equal to voltage times current times time divided by mass multiplied by change in temperature from new temperature costa 2 minus costa 1. So the specific heat capacity formula will be VIT divided by M multiplied by costa 2 minus costa 1. So this will be the final answer for part B. Part C states another student performs the experiment without using insulation. He obtains a higher value for C. Explain why this student measurements lead to this higher value. More heat lost to the surroundings, so temperature rise is less. That's why the value of C will be lower or higher. I mean higher over here. So that's why when there's a less rise in temperature, there's less rise in temperature, there will be higher value of below. So that's why the value of C will also be higher. Question 5 part A states two types of seismic waves are produced by earthquakes. These are called the P waves and S waves. P waves are longitudinal and S waves are transverse. Explain what is meant by the term longitudinal and transverse waves. So longitudinal waves mean in longitudinal waves particles of medium is parallel to the direction in which the waves are traveling. Whereas in transverse waves the oscillation of particles of medium is at right angle to the direction in which the waves are traveling. So this is the difference between longitudinal waves and transverse waves. Part 2 state another example of longitudinal wave, which is slinky springs, sound waves, ultrasound, and waves on water. Then transverse waves are ultrasound, water waves produce in electromagnetic waves and waves on rocks. So these are the examples of longitudinal wave and transverse waves. Part 3 states Part 3 states a seismic wave has a speed of 7.2 kilometers per second and the frequency of 30 hertz. Calculate its wavelength. So wavelength is equal to 7.2 multiplied by 1000, which is 7200. So then we will calculate V is equal to frequency times wavelength. Wavelength is equal to volume or V divided by what's this frequency. So the speed is 7200 divided by 30, which will be 240 meters. So this is what we will do in part 3. Now additional information of what are the examples, another examples that we just read for longitudinal waves and transverse waves. These include sound waves. For longitudinal waves, we have sound waves, ultrasound waves or slinky springs. Whereas on transverse waves, we have all electromagnetic waves, including light waves. Then we have water waves produced in triple tank and waves on ropes and waves on springs vertically. So these are examples for longitudinal waves and transverse waves. Part B states figure 5.1 shows an electric bell ringing in a sealed glass chamber containing air. So part A, this is figure 5.1. Now a student hears the bell ringing. The air is then removed from the chamber. State and explain any change in the sound heard by the student. So the answer will be no sound is heard outside the chamber because sound doesn't travel through vacuum. A medium is required for the sound to be transmitted. So this is why the sound cannot be heard by the student after the air is removed from the chamber. So this is what we will write in part B of question 5. Question 6 part A states figure 6.1 shows an object O placed in front of the plane mirror M. Two rays from the object to the mirror are shown. So over here we have two rays from the object, one over here and one over here. Part 1 states on the figure 6.1 for one of the rays shown, draw the normal to the mirror. So first we will draw a normal to the mirror for one of the rays. So over here we will draw a line which is the normal to the mirror. Then second states mark the angle of incidence, label this angle x. So we will mark this as angle x. Part 2 states on figure 6.1 draw the reflected ray for both incident rays. So first of this incident ray we will draw a reflected ray, and for this second incident ray we will draw another reflected ray. Now part 2 states construction lines to locate image O, label the image I. So now once we have drawn the reflected ray, now we will extend these both lines upwards to the opposite side until they join together, and the point at which they join is labeled or called I. So we'll mark this as I. So this is what we will do in part 1 and part 2. Part B states in figure 6.2 circular wavefronts from a point source in the tank of water strike a straight barrier. Part 1 states the reflected wavefronts seem to come from a single point. On figure 6.2, mark a dot to show the position of this point, label the point C. Now what we will do is over here mark the dot to show the position of this point. So what we will do is over here we will do a reflected ray like this, reflected water fronts from the barrier. So one over here and the other over here. Now we will mark this a dot to show the position of this point, label this point C. So this will be point C. Now point part 2 states draw and accurately as you can the reflected circular wavefronts. Now we will draw the circular wavefronts that will be over here on the same side, not on the other side, because here is a barrier and the wavefronts are reflected back. So this is what we will do in part 2. Question 7 states a small cylinder of compressed helium gas is used to inflate balloons for a celebration. Part A, Part 1 states in the box below, sketch a diagram to represent the arrangement of helium molecules in a balloon. So over here we will draw a circles for the arrangement of helium molecules in the balloon. So helium is a gas, so it will be away from each other. So over here, like this. So this is how we will mark the helium gas particles in the box. Part 2 states state and explain how the size of the attractive forces acting between the molecules of a gas compares with the size of the attractive forces between the molecules of a solid. Attractive forces between gas molecules are much smaller as compared to molecules of solid. So this is what we will write in part 2. Part B states the helium in the cylinder has a volume of 6 multiplied by 10 to the power of minus 3 meter cubed and is at a pressure of 2.75 multiplied by 10 to the power of 6 pascals. Part 1 states the pressure of the helium in each balloon is 1.1 times 10 to the power of 5 pascals. The volume of the helium is in an inflated balloon is 3 multiplied by 10 to the power of minus 3. The temperature of the helium does not change. Calculate the number of balloons that were inflated. So what we will do is first use the formula P1V1 is equal to P2V2. Now we have to calculate the volume of the two V2. So V2 is equal to P1 times V1 divided by P2. Now we have the value which is over here 2.75 times 10 to the power of 6 multiplied by 6 multiplied by 10 to the power of minus 3 meter cube divided by over here 1.1 multiplied by 10 to the power of 5 Pascal is equal to 0.15. Now what we have is 0.15 meters cubed. Now what we will do is 0.15 divided by 3 multiplied by 10 to the power of 5, 10 to the power of minus 3, which will be 50. So the number of balloons is 50 because each balloon over here is inflated to 3 multiplied by 10 to the power of minus 3. So if 0.15 is the volume, then we divide this by 3 times 10 to the power of minus 3. So 50 balloons will be filled or will be inflated. So the answer will be 50 balloons. Part 2 states later the temperature increases and some of the balloons burst. Suggest and explain why this happens. The answer will be pressure of the air in balloon increases because molecules move faster, which causes the balloons to expand and finally burst. So this is what we'll write in part 2. Questions 8 states a charger for a cell phone or mobile phone is marked input is this and output is this. Part A states part 1 the component in the charger that converts AC to DC is a diode. So the answer will be a diode. Part 2 states a quantity that has the value of 50 Hz. So the frequency of an AC supply is what that will have a value of 50 Hz. Part B states part 1. Calculate the output power of the charger. So pressure power is equal to volume times current. So the volume is here voltage, I mean voltage. So voltage is 0.5 multiplied by 5.3, which will be 2.65 watts. So the output power is 2.65 watts. Part 2 states the energy transferred in the output circuit when the cell phone is charged for 1.5 hours. So energy is equal to power times time. So the power is 2.65 and the time is 1.5. So 2.65 multiplied by 1.5 multiplied by 3600, which is 14,000 joules, because we converted 1.5 hours multiplied by 3600. So this is how we will calculate the energy transfer. Now part C states the following list underline the quantity that is stored in the battery of the cell phone. So the quantity that is stored in the cell phone is the energy. So this will be the final answer for part C. Question 9 states a technician sets up a radiation detector in a university laboratory for use in some experiment. Even before the radioactive source or the equipment is brought into the laboratory, the detector registers a low count rate. Part A states suggest what causes this count rate. So the answer will be background radiation. Part B states a radioactive source that emits alpha particles is placed in the laboratory bench and the source is gradually moved closer to the detector. At first, the detector continues to register a low count rate, sometimes slightly less than the count rate registered without the source. The count rate suddenly increases to a very high value when the source is very close to the detector. Explain these changes in the count rate. First is the low count rate is due to the background radiation or background radiations only. Second is slightly less reading due to random nature of radioactivity. Last is very high reading due to alpha particles. So this is what we will write in part B of question 9. Part C states in the second experiment alpha particles passes between two parallel horizontal metal plates in a vacuum. They then continue to detect. They then continue to the detector as shown in figure 9.1. So over here a positive charge is established on the upper plate and negative charge on the lower plate. In part 1 on figure 9.1 sketch the new path of the alpha particles. So what we will do, the new path of the alpha particle will be towards the negative metal plates like this. So this is what we will do in part 1. Part 2 states state what happens when the count rate registered by the detector. So what happens to the count rate registered by the detector? So the count rate decreases because the detector records background radiation, because most of the alpha particles moves towards the metal plate. So only the background radiation is being recorded by the detector, so the count rate decreases. So this is what we will write in part 2. Question 10 part A states in a room in a house there are 4 electric lamps in parallel with each other, controlled by a single switch. With all the lamps working, one of the lamp filaments suddenly breaks. What if anything happens to the remaining lamp? Explain your answer. Nothing happens because they stay on with some brightness, with the same brightness as before. They had the same voltage as before because they are connected in parallel. So this is what we will write in part A. Part B states in figure 10.1 shows the circuit diagram of the lamp in another room. X and Y are two-way switches. Part 1 states complete a table by indicating whether the lamp is on or off for each of the switch. If the position of X is 1 and position of X is 1, the state of lamp will be on. When X is at 1 and Y is at 2, it will be off. And when X is at 2 and Y is at 1, it will also be off. But when the X is at 2 and Y is at 2 also, then the lamp will turn on again. Part 2 states explain why this arrangement of switches is useful. We can operate the lamp by any of the switch. So this is what we will write in part 2 of question 9. Question 11 part A states the names the process that causes a potential difference across a solenoid due to the movement of a nearby magnet. So the answer will be electromagnetic induction. Part B states figure 11.1 shows a solenoid connected to a center 0 voltmeter amp. A bar magnet is held with its north pole close to one end of the solenoid. So over here we have the north pole side facing towards the solenoid, and this is the figure 11.1. Part 1 states the magnet is pushed into the solenoid and then brought to rest with its end pole just inside the solenoid. Describe the movement of the pointer of the meter amp. So the answer will be pointer of the meter deflects to the right and then returns back to its original position. Why? Because the pole or the bar magnet just moved once into the solenoid and then it's at a resting position. So this meter will deflect to the right side and then return back to its original position. Part 2 states magnet is now pulled out to the left of the solenoid at a higher speed than in part 1. Compare the movement of the pointer of the meter with that seen in part 1. Answer will be the pointer of the meter shows greater deflection. It deflects in opposite direction and returns to 0. So what this basically means that at first the bar magnet has been moved into the solenoid slowly, so the meter deflected little bit to the right. But when the bar magnet was pulled at a higher speed, so the reading showed a greater deflection than before. So this is what we will write in part 2 of question 11. So guys, if you like this video and are clear with these questions and topics, don't forget to subscribe, like this video and share it with your friends. Thank you. See you in the next video.